All right. Thanks everyone for coming out. Thanks for Sean for inviting me up here. So anyway, yes, my name is Dan Simon. I am a senior engineer at Tumblr. I've been at Tumblr for almost 3 years now. I've been doing Scala development the whole time there. So today I'm going to talk to you about our work in building microservices at Tumblr and also the Colossus framework, which we have been working on for about a year now. And we recently just open sourced about 2 months ago. So just to kind of set things off, when we talk about a microservice, what are we even talking about? And I think microservice is a little bit of a buzzword. I actually didn't even hear that term until fairly recently, but it kind of describes what we've been doing fairly well, so we stuck with the term. Basically what it is it's a small single-purpose application that is mainly designed to encapsulate a single feature of a larger application or system. Usually they're stateless. They don't have to be, but certainly most of the ones we're building are stateless. So they'll interact with one or more databases or caches, and they usually work with some commonly used protocol like HTTP. So I have a very rough diagram of what kind of the flow of a microservice would look like. You have clients who connect to the service. The client sends some kind of request. The service will usually do some kind of processing on the request, and then in turn send one or more requests to one or more databases or caches or maybe another service, and it processes the response and then sends a transformed response back to the client. So this is usually the workflow we think of when we think of a microservice. Now, obviously this can apply to a lot of things. You could apply this to a database or to a RESTful API or to like a whole website, but usually when we use the term microservice, we're talking about something that is mainly on the back end and is lower level than something like a full RESTful API. And I'll have some examples pretty soon about what exactly we're doing. So to give high-level examples of the kinds of services we're writing at Tumblr, they largely fit into two families. The first is application layer routers, and this means basically having a proxy or a load balancer that understands a higher level protocol, something higher than TCP. So we're talking about either HTTP, we could be talking about the Redis protocol, or some task messaging protocol, something that allows us to make more intelligent decisions about where to route things or where to proxy things, more than you would get out of doing it just through TCP routing. The other example is what we call database abstraction services. And these are basically designed to take some database or set of databases or caches and provide a simpler interface over a more common protocol. And in our case, it's designed to make it easier to work with from PHP because for the most part, and we'll get to it here, just as a quick overview of the architecture that we have at Tumblr, we are mostly a PHP application. So the vast majority of the website is written in PHP. We've been trying to move things into Scala services for quite a while. We have maybe about a dozen or so of them that are in production. And these are the databases that we most frequently work with, so MySQL, Memcached, Redis. We have a few HBase clusters. We use Kafka for the Tumblr Firehose, and we have a few others as well, but these are the big ones. So one of the big goals is to basically hide a lot of the details of these protocols that these databases use from PHP and provide something simpler, just like HTTP or other simple protocols like that. So we've been doing service development for quite a long time, basically since before I started even. And probably for the first 2 years, like from 2012 until about this time last year, we had really mixed success with building microservices. So up until that point, we had largely been using the Finagle framework from Twitter, and which mostly using the Thrift protocol for the services. And while we were able to build things that performed fairly well, some of our services would be doing many thousands of requests per second, serving features for the website itself. So if you go to your dashboard, you go to a blog, the actions that you're doing are directly hitting some of these services. But we had a lot of problems as well. We found that between both learning Scala and also learning Finagle, there was a very big learning curve. So there was a pretty small number of engineers who were even able to work on these things at all. So to give a rough idea, we've scaled up over the last few years from maybe about 50 engineers to about 120, and maybe 5 or 6 of us are doing service development. The other things we found that we ended up writing a lot of boilerplate code, even for very simple services. A great example is we had one service that would basically just increment counters in Redis, and this ended up being a fairly large Scala application for something that should be very simple. And in turn, because of this, it made the code difficult to maintain. It ended up leading to lots of instability problems in production. Anything from like GC pause issues to just flat out crashes. And then a big issue for us specifically was that using thrift from PHP has a pretty significant performance overhead. PHP is an interpreted language, and even when we use code caching and things like that, just to get all of the thrift bindings loaded and usable has a fairly significant overhead, and it made it really difficult to move towards a more service-oriented architecture. So about a year ago, or a little over a year ago, we really kind of decided to start from scratch again, or not entirely from scratch, but we really took a hard look at what we were doing, and we kind of decided to throw a lot of the things out that we were doing and start over. And that process is basically what led to the development of Colossus. So right from the get-go, we wanted to build something that was optimized for very low latency, high throughput, small requests, the kinds of things that we do in our microservice. Most of our services are not serving large amounts of data. They're very simple requests, just like grab an integer or grab a very small JSON blob or something like that. So we wanted something that was super optimized for these situations. We wanted something that was a bit more minimalist than what we've been doing with Finagle. I think part of this was because if you're not familiar, Finagle itself is a very large framework, and it is in turn is built on the Java Netty framework. So trying to wrap your head around both of those, especially when things started going wrong, was very difficult. So we wanted to take a different approach to build something that did really only what you wanted, and we wanted to do that very well. So sort of taking like the Unix philosophy, where just build the things that we want to do and make sure it works really well for those situations. Another thing that we wanted to do was to have more compatibility with the typesafe stack, which when we had started developing services, that didn't really exist, but has since become much more popular. So we have begun using specifically the Akka framework much more, and we wanted something that was built on top of that and could interact with a larger actor-based application. We wanted something that was modular and flexible, so if we wanted to build something very high-level and abstract, you could do that, but if you really need to go in and do some performance tweaking or optimizations, the framework didn't wall you off from doing those kinds of things. And of course, we wanted something that was 100% Scala. The gist of how Colossus works is it takes a approach to doing non-blocking event-based programming. So this is similar to sort of how something like Node.js works, or in the JVM there's another framework called Vertex. They all work fairly similar, where you have one or more event loops, which are sort of constantly spinning and processing events that come in for server connections. And then you, as the person writing the application, writes very low-level connection handlers that attach to these incoming connections, and they process any data coming in. They can write on the connection, and they can handle the very basic events that you deal with when you're working with TCP connections. So we want to take an approach like that, and then to bring the whole Scala and Akka thing into it, we made our event loops actors. So we're normally in an event-based framework, your event loop is literally just a loop that is, basically just talking to the operating system and looking for events. Our event loops are actually actors that, to do the looping, they just send messages to themselves. And what this lets us do is this lets us take these low-level event loops and integrate them with something that is built around Akka actors, where everything is done through message passing. And it allows you to kind of get the best of both worlds, where when you need to write very low-level, high-performance code, you can do that directly in the event loop. And when you need to move to something, if you're using a blocking API, if you need to access some kind of global shared state, all the things that actors are meant for, then it's very easy to hook those into your service. So the results of this is, for the services that we're writing, most of the code per connection is single-threaded. So this is similar to the kind of situation that you would have in something like Node.js, where everything you do is single-threaded. The big difference is, of course, we're running multiple event loops, so we can already immediately scale out to however many cores your machine has. And that's something we take a huge advantage of, because most of the machines we use in our data centers have anywhere from 12 to 24 cores. So that's a huge advantage it gives us. We provide what we call the callback monad. So this is something that's like a future. For any of you who've worked with futures, it's just a way for doing concurrent programming. So our callback monad works very similar to futures. It has all the same methods like map, flat map, recover, things like that. But it's entirely optimized for doing things in the event loop, which means that everything it does, it keeps it all single-threaded. It never uses execution contexts or anything like that. So it's very optimized for situations in our services where basically, let's say you have incoming server connections, from your clients, and on the other side you have a connection to, a cache or a database. What we can do is we can basically pipe data from one to the other. Sometimes with you're reading in the data and doing a transformation, but in some of our cases we're literally just piping things from one side to the other. And in those cases we can do that now without ever having to do any kind of like parallelism. Things can basically just be read in, immediately written out to the database, and then read back from the database and sent back to the client, all in a single thread. And that makes things very, very low latency, and there's very little overhead in doing that kind of thing. And the last point here, this is actually something we're working on right now, is for things where you're piping data back and forth, we can actually do this without having to pull the data into the JVM heap at all, which is really good for trying to keep your garbage collection rate low. So the end result for all this is we have very low latency for small requests, and I'll get into some examples about what exactly these requests look like. But the takeaway is we can write services that can do hundreds of thousands or even millions of requests per second on a single machine, and still keep very low latency. We're talking a few milliseconds. We're not wasting overhead on unnecessary parallelism. So like the situations I was talking about, we are basically just shoving data from one connection to another. There's no need to jump threads or use futures to do anything like that, because you're basically just reading data in from the network card, sending it back out. So we can kind of avoid those situations when we don't need to. And of course, one of the big criticisms of a lot of event-based programming frameworks is what we call callback hell, where that's a situation where usually you would call some function and you pass another function as a continuation, basically saying when you finish your event, run this function, and that often ends up in these very large sets of nested functions. And since we're using the callback monad, which is very similar to how futures work, everything we know about how to work with futures, you can just apply to callbacks for the most part. And so the big thing is this allows us to write low-level code, but also mix in actors and futures when we need to. So let's actually take a look at some code. Okay, so that's not showing up too well, but luckily we have our trusty Vim. So can everybody see that? I can make it a little bit bigger. All right, so this is what a basic kind of hello world service is going to look like. So what this is doing is we're basically spinning up what we call an I/O system, and that's basically just starting up your event loops. There's a lot of configuration. We're just using all the defaults here. And then what we're doing is starting up a service that is using the HTTP protocol and it's going to be listening on port 8080. And then we have a bit of a DSL around starting this whole thing up. So this is basically the simplest way to do it. And you can see all we're really doing here is we're calling a single function and passing a pattern matching expression to it. And then we're just using another DSL to basically pattern match on the incoming HTTP request. And then, so for this first line here, we're just looking for, just like the /hello URL. And then you can see what we're doing is we're creating a response, this is basically just going to be a standard, 200 HTTP response, and then we're wrapping it in a callback. So if you've worked with futures, this is very similar. We're basically just creating a callback that is done immediately. And then the second request here is we're sort of just showing that you can take things out of the URL and just put them back into the response. So this is a very, very simple example just to show what the flow kind of looks like. And this is not very interesting because we're not really taking advantage of the full power of what you can do. So we'll look at this next example, which now we're basically, this is starting to look a bit more like what we actually do, is we have a service that is using HTTP again, but now it is connecting to a Redis server, and it's basically just, I implemented half of like a get set for just getting a key from Redis. And so there's a few interesting things to look at here. The first thing is we changed the function that we're calling. So here we use service.become, which is like a very, very simple version. Now we're using service.serve, which is more of like the full-featured version. And you can see there's a couple nested functions here that we're given. So the first one allows us to do initialization per event loop. So basically everything that's happening here is going to be happening once per event loop. So if you start up, let's say you're running on a machine with 10 cores, your service is going to start up by default with 10 event loops. So what's going to happen here is when we have this line here creating our Redis client, it's actually going to be opening 10 connections to Redis, one per event loop. And this, if you remember, I mentioned that event loops are actors. And this, if you're familiar with working with the Akka framework or with actors in general, you know one of the very important things is you do not share state between actors. And here we're doing that by basically duplicating the state in situations where that's okay. So for here, it makes complete sense to basically open 10 connections instead of one. This way, each event loop has its own connection to work with. We don't have to worry about any kind of thread locking or message passing to do that. Since each event loop is single-threaded, when a single client connection is being processed, it has exclusive access to the Redis client just because it's all single-threaded. So then here what we're doing is this part right here, we are setting up basically what we were setting up in the first one, what to do for each individual connection. And so this time we're actually given a handle to the connection, and then we tell the connection to use this pattern matching sequence. Again, we're basically just pattern matching on the URL. We're getting a key, and then what we're doing here is we are using our Redis client to send a command to Redis. And what's happening here, actually, I changed this a little bit in the slide, but to give you an idea what's happening here is we're actually getting back a callback from Redis. So this is really something like this. And then that's what's really happening. Oops, I spelled that wrong. So when we call redis.send, we're getting back a callback, and the easiest way to think of a callback, I describe it as sort of like an in-thread feature. It's really more like a function builder. So when I call this redis.send, it actually hasn't sent the command yet. It's basically just given us a way for composing what to do when it actually does send it. So then we're just mapping on it, and we're basically just processing the reply from Redis, and then just sending that result back through HTTP just as a string. And then what's going to happen here is when we return this callback back to Colossus, Colossus is going to take over. It's going to actually do all the execution, and it's going to actually send the command. So this is how we can do non-blocking I/O and keep everything single-threaded. And then lastly, to show what it looks like to work with futures and actors, You can see up here I've defined just a very simple actor that basically just generates unique IDs. And the way it works is whenever it receives this string as a message, it's just going to increment its local ID, send that ID back to whoever sent it the original message. And then down here we are just creating an instance of that actor. And then here again we're creating another service. Very similar. The one big difference here is you can see we're importing something here called callback executor, and that's basically a way that we can take a future and sort of reroute that future back into the event loop after it's completed. So the way this service works is we are receiving, again, another HTTP request from the client, and then what we're doing is we are, right here, we are sending an actor message to this actor basically saying, give me the next ID. And we're wrapping this in a callback.fromFuture. So what's going to happen here is we're going to send the actor message. The actor, which is running on a different thread, is going to receive the message, increment the ID, send back another ID. But the sender, again, this is bringing back that I mentioned that event loops are actors. So what's happening here is this sender is actually the event loop that is basically containing the connection that sent it. So what's happening is the sender is going to send this ID back to the event loop. The event loop is going to realize that this message is actually meant for this individual connection who sent the original request. It's going to then basically pick up where it left off, where this map is, and again transform the ID back into an HTTP response, send it back to the client. So what we're doing here is we're going from the event loop outside into some other thread where the actor is running, and then going back into the event loop and out to the network. So these situations really cover most of our use cases in the real world, where most of what we do for our very low-level stuff, especially when we're working with either Memcache or Redis, where when it's really important to actually really get tens of thousands of requests per second, doing everything in thread like this actually has a huge advantage. And then for other situations where we're talking to, say, MySQL or HBase, which are naturally not as fast as Memcache, and we're not going to be hitting those as often, then it's totally fine to sort of jump out of the event loop, do whatever processing we need to do the same way you do with any other system, and then go back in and send things back to the client. All right. Great. So let's talk about some actual services that we've written. So the first is a system called Rediscover. This was actually the use case that led to the development of Colossus. So basically what this is, it is a dynamic Redis proxy. So what we do is we have a lot of Redis. We use Redis very, very heavily. It serves a lot of many of the important features on the site that the throughput would be too high just to hit MySQL directly, but require more structure than just Memcache. So what we do is we build Redis into clusters of anywhere from like 10 to several hundred individual instances of Redis, and then we put these proxies in front of them to do all of the consistent hashing to evenly distribute all the keys across all of the Redis instances. So it doesn't let us use every single Redis command. If you're familiar with Redis, it gives you all kinds of crazy commands for doing like set intersections and unions and transactional stuff. We don't use a lot of that. We mainly use just like key set and get. We use lists and hashes and things like that. And this gives us the ability to use all those. And the big thing is it gets all of its routing information from Zookeeper, and we actually have a whole management system that allows us to set up clusters dynamically. It monitors all of the Redis instances and lets us do things like automatic slave promotions. So some of our more important clusters, we have master-slave setups where Redis is automatically copying all the data to a slave. And then if we have a situation where the master crashes or there's a hard drive failure or something, this can detect that very quickly and immediately swap the slave in and keep things running smoothly. So this is a situation where really needed the high performance of Colossus. And the very first version of Rediscover was written, in Finagle, and it used the Redis protocol. And the Colossus version is anywhere from like 4 to 5 times faster. So we can easily get like 250,000 requests per second on a single machine. And these are not the most powerful machines. We have others that are even more powerful. But this was sort of the case that led to building Colossus, because we realized it was a very large project for something that should be not that large. And obviously, we weren't getting the kind of performance that we wanted. So what I ended up doing is I rewrote Rediscover basically not in any framework. I was using just Java NIO directly. And then that ended up working very, very well. And then actually during a hackathon, in 24 hours, I took that and turned that into like what became the first version of Colossus. And then that was shelved for a little while, and then we pulled it out thinking we might try to use it for something else, and it worked extremely well, so now we're using it in more and more things. So one example of where we use Rediscover is right here on our search for type ahead. So as you are typing into the Tumblr search, it is hitting a fairly large Redis cluster, basically giving it your prefix, and it's just returning immediately some pre-calculated search results. And this was actually an area where we needed the high throughput again, not just for reading the data, but actually for updating this, because this data is calculated from a Hadoop job that is obviously doing all the heavy lifting of coming up with all these pre-populated lists. So it has to get all that data into Redis without doing any kind of like snapshotting or anything like that, because we can't stop the instances from running or do any kind of large-scale loading from disk, because that would affect performance too much. So we just basically load all the data in, but just by calling set a million times. And the faster you can do all that, the faster you can update your index data and keep your search results relevant. So here's another example. Activity pages. This is something for our users, basically to get some very basic analytics on their blogs. So if a user makes a post and some people like the post or reblog it or something, they can kind of get a summary of what's happening on their blog. So this is a slightly more sophisticated service. It's actually talking to 2 Rediscover clusters as well as an HBase cluster. So it's using the Redis clusters basically as caches, and then HBase for its long-term storage. And this is a good example of where we're sort of doing that mixed of inside event loop, out event loop processing, because most of the read requests can stay right in the event loop, just hitting Redis, and those are very, very fast, a millisecond or 2 at most. And then for all of the write operations or for cache misses, then we can use futures basically to hit HBase, which generally has a much higher latency, so we want to do that out of thread, obviously. So that gave a pretty good overview of the basics of what Colossus is and why we built it. There's a bunch of other things I didn't mention. I've been talking this whole time about using Colossus for microservices, but it's really a fully generalized I/O layer. So some of our work right now is actually starting to write other abstractions besides sort of like the request response system you have for services. But if you wanted to, you can actually just write something on top of that lower layer and do whatever you want. If you have something that doesn't fit that paradigm, you can take this and do anything you want with it. Another important feature is everything we do in Colossus has the ability to track real-time metrics. So we're talking about things like request rates, latency. You can define your own. So all that is built in. It can do aggregation, and it can also forward metrics periodically to some external system. So we use OpenTSDB for time series processing, and we rely on that extremely heavily for health checking, for just seeing how things are doing. So we have thousands and thousands of metrics going into that. So this makes it really easy to pipe all that data into OpenTSDB and then get some nice graphs and see like how is our services performing. Some other cool stuff is we have streaming parser combinators. So this is if you've ever worked with parser combinators, it's basically a way of taking tiny small parsers and wiring them together to be able to parse, some kind of grammar or language in a very, easy to understand fashion. Usually, your parsers basically look like just a formal grammar specification. And so we created our own parser combinator library, which is what we use for all of our protocol support for like Redis and Memcache and some others. So this makes it really easy to write parsers, and the big thing for us is that they perform very quickly for the kinds of stream processing stuff that you usually deal with when you're dealing with network protocols. And lastly, we do have a small but slowly growing test kit to make writing unit integration tests for your services a lot easier. So similar to the way like Akka provides its own test kit for being able to test actor-based systems, we kind of leverage, write some stuff on top of that to make it easier to test Colossus-specific things. So the last thing I should mention about Colossus is we open sourced about 2 months ago, and we are still very much in a pre-1.0 state. So we are using it in production, as I've shown. We're using it all over the place now. I mean, I would say that overall Colossus in production has processed several trillion requests at this point. But we are still really heavily working on adding better protocol support. So we're trying to write native support for things like MySQL, Cassandra, MongoDB, things like that. We're trying to add support for multiplex services. So this is basically when you can return responses in different order that the requests came in. And this is something, for example, that HTTP2 does. We're also adding better support for streams. So this is actually very important for us because we're starting to write some services that deal with larger sets of data. For example, images. So like right now, all existing services, if you want to build a response or process a request, you have to load the whole thing in memory at once before you can use it. So we're trying to add support where you can basically stream that data in, such as an image, without destroying your memory. And of course, we're always working on API improvements. Everything I showed you, the whole DSL and everything is we're constantly tweaking. We're trying to make it easier to use because that's one of our big goals, is to keep this straightforward and easy to use, especially in our situation because we're trying to get some of our PHP programmers to start learning Scala and write services for us. And trying to lower the barrier to entry is a very big deal for us. And lastly, the last thing I should say is I mentioned that building Colossus was part of our steps to make writing services easier. And it's certainly dramatically helped us. We went from a situation where we only had a few services that were constantly having problems to really being able to scale up and actually really move towards a service-oriented architecture. But there's a lot more to it than just having a good framework. And these are some of the things that we found that are extremely important to have. So development consistency. You want all your services. We don't really enforce specific styles too much, but we are trying to keep a relatively unified way of doing things. Testing is extremely important, not just unit or local testing, but also having a full testing environment where you can make sure that everything works from end to end as you would expect it to. Deployment is a really big one, especially when you're talking about having a bunch of different services running on several machines. We have Colossus services running on, I don't know, 50 to 60 machines, probably more than that actually. And just getting the service up and running on your servers is a big deal because you need to make it easy. You need to make it generalized so you don't have to do the same thing over and over again for each service. So we think actually this is a very heavily area of research for us. We're actually looking into things like Docker and other containerized systems for making it easier to do that deployment. Service discovery is another big one. That's basically if you have a situation where services are talking to each other, they need to know where they are. Again, this is something that we are very heavily researching. This is something that we've been using Zookeeper a bit for. Like I mentioned with Rediscover, Zookeeper contains all of the information to tell the proxies which Redis instances to talk to. We're also trying to look into using that for basically which services to talk to for our other services. And then lastly is monitoring. So you really need to have a way for if a service starts to have problems for any reason. It could be anything from a hardware failure to a bug or anything like that. You need to have lots and lots of insight to be able to see what is happening in production, and also to be able to get alerted as quickly as possible when something goes wrong. So we have a very large setup now where, like I said, we have OpenTSDV for all of our metrics. We're using a system called Isinga, which is sort of our monitoring alerting system. And then all that is wired together, and we're using PagerDuty. So basically, if one of our services starts having trouble, we can usually get alerted within a minute or so of it having problems. So I think that's about all I have. I'm going a little bit over time, but I guess thanks everyone. We have time for questions, maybe. Yeah, for sure.
For example, if I wouldn't come here today and I would like to write a microservice, I would go and use Spray or HTTP and some headers, and I'm done.
Mm-hmm.
It's more components that you just mentioned in the last slide. What would be the benefits, or what would be the reasons why I would go for Colossus rather than the plain approach?
Right. So just to repeat the question, why would somebody choose Colossus versus something like Spray, which is a pretty popular framework? And I should mention that we actually use Spray internally. The Tumblr firehose is written on Spray, and it works extremely well in that situation. The things that Colossus is really meant for is lower level, very low latency kinds of requests. So I should mention that when I was in the process of sort of trying to figure out what to do with Rediscover, when we moved off Finagle, I had tried writing it on top of the Akka.io system, which is basically what Spray is built on. And it was certainly much easier to build it, but we didn't really get a huge performance improvement. It was a bit better, but not as good as when I basically dropped all the frameworks and just wrote it straight on NIO. So in terms of looking at Colossus versus Spray, that is one of the factors. Another factor is the protocols. So all my examples here are using the HTTP protocol, but we're actually probably going to stop using HTTP for our backend services. And one of the protocols we're looking into actually is the Redis protocol. And one of the reasons for this is the Redis protocol is much thinner than HTTP. It's much easier to parse, it's much faster to work with, and we have very, very good support for it from a client perspective. So basically every language, PHP, Ruby, Python, they all have Redis clients. So we're actually looking into using the Redis protocol in situations where we would use HTTP. And I should mention that the Redis protocol is actually a fully generalized protocol. It's very simple. Basically, just gives you a way of sending a set of bytes and then sending back a response that can be like just raw bytes or like a list of sets of bytes and things like that. And in a lot of our situations, we're basically we don't have services that have complex URLs. We don't deal with headers or cookies or anything like that. We basically just need to say, send this command and then get back a response, which in a lot of cases is either like just an integer or a very small JSON blob or something like that. So I think that in a lot of cases, HTTP is a bit of overkill in that situation. But regardless of whether you go with HTTP or Redis protocol, we have support. You can basically plug in whatever protocol you want into and choose whatever you want for whatever situation you have. So I would say those are the two biggest reasons. But yeah, we use Spray internally, and for the things that we use it for, it works very well. Yep.
Do you have any measure of how much performance degradation there's been since switching from the raw NAO stuff that you did to Colossus frameworks?
It's hard to say because the raw NIO version that I wrote was probably not super optimized. So I guess the overall is that the Colossus version is actually faster. But I would say I don't think there's, if I was to rewrite in raw NIO, I don't think there would be much of a performance difference. One of the things about writing code like this and having these event loops is there's very, very little in between raw NIO and your event handling code. In most cases, it's basically 1 or 2 function calls. And that was one of the big goals I was going for, is that I don't want this to be significantly slower than just writing it directly on NIO. And I think that's, for the most part, that's the results that we've gotten. Yep.
How's it going at Twitter getting PHP programmers to write in Scala? And because I think you're a top coder, and the top coders produce these code bases, and then it has to go out to maintenance, maybe offshore, to the team. And then you've got some managers with trouble getting staff.
Yep. Yeah, so...
What kind of wind is blowing?
Yeah, so that's actually been something we've been dealing with for basically as long as I've been to Tumblr. Trying to teach PHP developers how to write Scala, and I think more on top of that, getting people who are primarily product engineers who mostly focus on user features and business logic, how to get them to focus more on lower level performance and concurrent programming, because PHP, you never deal with threads really. You never deal with having to worry about whether something is blocking or non-blocking, because everything is blocking basically. So the basics is it's tough. It's really tough, and like I said, we have now roughly 100, maybe 100 people who are regularly doing PHP development, and there's maybe about 7 to 8 of us doing Scala, and I would say things are getting much better now. We have a lot of people who are very interested. It wasn't always that case. There was a bit of a divide for a while where the PHP developers would be working on some new feature for the site. They would realize, oh, we need something that runs outside of PHP, and they'd come to us and they'd basically tell us to write it. Now we're moving towards a situation where we work with them to have them build it. And then when it comes to maintaining it, we do have like a site reliability team. We have an operations team, and again, it's working with them to show them how things work, and for common situations, what are the courses of action to take. That really fits in line with what I was talking about with development consistency, because one of our big things is when you're building a service, you must write documentation for it. You must explain what it does, the very basics of what it interacts with, and things like that, so we can hand it off to somebody else. So if 2 a.m. something goes crazy and we have on-call engineers, the goal is for them to be able to at the very least figure out what's going on and rope in the relevant people rather than just call everybody and freak out. Yep.
So I'm actually using Scala, and in our stack, it's like half of it is PHP, half of it is Java. So what makes Scala good for microservices, and would you recommend it for? I know a lot of services that have very high volume and high requests use it, but what if you just have nothing
right.
super crazy?
Right. So if you're in a situation where you're not too concerned about performance, I think you have a lot more flexibility in what you choose to use. So if you're talking about using Scala versus something like Python or interpreted language, I think if your throughput is low enough, and especially I think the big thing is if you're more familiar with that, then especially as a first version, I don't see any reason why not. I think it fits a little bit in line with you usually don't want to try to prematurely optimize something, but let's say comparing Scala to something like Java or maybe to Go or Rust, which is getting more popular now. I think again, part of it comes down to what you're familiar with. So we experimented trying to do some stuff in Go, and we found it's an easy language to learn, but it's not as easy when you're trying to build bigger things and you're trying to get used to a whole new system. So we stuck with Scala. I think it gets a bit more fine-grained about what the differences between all those languages are. I like Scala because it lets us do all this stuff in a very expressive and simple way. So when we have these very thin DSLs where basically you're calling one function to spin up a service, that's sort of something that would be a lot more code if you're trying to do it in any of those other languages. So for me, I think that's one of the big reasons. And at the same time, it lets you take advantage of all like the optimizations that the JVM does. It lets you work with Java libraries when you need to. It does all that stuff for you. Yep.
So maybe just one more question,
Yeah.
and then we'll roll on to the next talk. There'll be a social afterwards. If you want to stick around,
I'll be here. So.
Lots of opportunities to talk. So go ahead with. I think it was.
Oh yeah, I think you're first. Yeah.
Okay. You mentioned that you wrote your own parser commutator library. And is the metrics library also? And are you going to split those out from Colossus, or are they already?
So the metrics library is it's already packaged as its own jar, and it doesn't depend on Colossus. I would say at this point we haven't put nearly as much effort into making that a clean API as we did with Colossus itself. So that's why I didn't really show off any examples with it. It's certainly something we're going to work on more. And for the parser combinators, I guess if we get interest in that, again, those are very self-contained. So yeah, it could certainly happen. Cool. All right. Thanks, everyone. Right. Probably.